All right, everybody. Thank you for joining today. Today I have on the line our customer-facing data scientist, Dave Henneke, and AI Success Director, Kamesh Bamu. We'll be discussing today reducing cost with predictive maintenance, part of our model building webinar series. As a reminder, all of these are recorded and hosted on our community website. And from there, you can ask additional questions if needed. At any time during this webinar, feel free to ask a question at the webinar, and I will relay that to Dave and Kamesh to get an answer. And if there's any questions, please feel free to email at aisuccess-webinars@datarobot.com. And with that, I will turn it over to Dave and Kamesh. Thank you.
Okay. Thanks, Regan. Hello, everyone. I'm Kamesh Bamu. I'm an AI Success Director at DataRobot. And I help customers, DataRobot customers and users think about the best ways of getting value from the DataRobot platform. And oftentimes it starts off by asking a question, what are the use cases for their industry? Prior to DataRobot, I spent more than 19 years in the industry, including a number of years in manufacturing and industrial environments, where predictive maintenance was a very high impact AI use case. So really excited to be doing this webinar with Dave. Dave, good morning.
Morning, everyone. This is Dave Henneke. I'm a data scientist here at DataRobot. I got my start as a mechanical engineer, and gradually over the course of my career, I've moved from mechanical engineering into a role as a data scientist. So this is a great use case. It's one that kind of ties most of my past experience in engineering to kind of my current work as a data scientist. So one that I really love working on. A lot of different examples that are great mechanical engineering problems to work on. So excited to take a deeper dive today.
Thanks, Dave. So in today's webinar, just to set the context, we will be talking about predictive maintenance. It's actually a much researched and discussed use case for a number of industries. So for this discussion, given the time limitation and the format limitations, we will focus on certain elements of this, primarily laying out the foundation for why we are talking about this use case, the kind of modeling approaches that we recommend customers think about, as well as how to prepare data. And along the way, Dave and I will discuss some of the common issues and challenges that we see our customers face and how to navigate that. So with that, let's go to the next one. So let's start off by discussing what is predictive maintenance. So for most manufacturing and industrial companies, there are a number of assets that are deployed in the field. Sometimes these are oil pumps in an oil field, manufacturing equipment in factories, engines in airline industry, or even the more familiar examples of transportation and school buses. What all of them have in common is that they are assets that need equipment maintenance. Historically, this has been done through periodic maintenance. For example, all of us are familiar with oil changes that we do at 3K or 5K intervals. In certain cases in the industrial environment, there's also inspection of equipment. The AI use case is mainly focused on moving from a reactive to more of a proactive approach to maintenance. In addition to the existing processes, sometimes AI use cases are used as an additional decision support tool. And the decision is usually when to change a part, for instance, or what kind of intervention to do, for example, change an oil or air filter, etc. And essentially, AI comes in helping identifying potential failures ahead of them happening. Next slide. So we usually start off by discussing what are the benefits of predictive maintenance. And as I said before, there are a number of industry segments that all work with predictive maintenance. And what we see for most of our customers, the benefits are one of four different kinds. One is an asset uptime, which is you can ensure that the asset is up and running. For example, an oil pump that's generating hundreds of thousands of dollars every hour. Every hour that you can contribute to it staying up and functional without a degradation in performance can result in benefits to the company overall. There's also reducing costs. The costs are primarily around service maintenance, maybe spacing out the intervals better, avoiding part replacement costs, all of those benefits. The third element is safety and health risks. In an industrial environment, the risk factor is monitored very closely, and AI can really help identify some of the potential risks and then, of course, bring the overall risk factor down. And then finally, for most of these equipment, the asset lifetime is a significant factor. The longer you can keep an asset working without degradation in performance, the better it is for the overall cost of ownership. And this is where AI can be a pretty important tool. So one of the first things we discuss at this point is you've got a customer that's probably has made the call, predictive maintenance is important for their use case. The next question is, what data sets do we have available? And what we see are some of these kind of example data sets. In today's digital world, most of the technologies, industrial environment, equipment, etc., they have what's called equipment sensor data. So these are digital sensors that are capturing all of the analog information surrounding the equipment. Typically, this is captured in control units, control modules, telematics, and other such means as well. And over time, as you collect more and more of the sensor data, it can be a pretty valuable source of developing an AI use case. The second kind of data set is parts performance data. And these are for most industrial organizations who have built significant organizational IQ around how to do quality regularly, warranty records, field performance data. All of these can become an important source of information as well. The third data set is service and maintenance records. As we talk about AI in predictive maintenance, the service and maintenance part becomes a very important and a valuable data set to work with. This can be a source for identifying the current state as well as potential future state benefits. And then finally, all of the AI use case, predictive maintenance use cases are working within an environment where the environment, the ambient information can be pretty valuable. For example, in peak summer in Arizona, it might be a different environment compared to winter in Alaska, where it's a completely different environment. So just knowing that context can really help us develop a really good understanding of the operating conditions. So Dave, at this point, what are some of the examples or use cases that you see customers think through?
Yeah, so it's interesting. Predictive maintenance is really this umbrella term that can refer to a whole bunch of different use cases. So, for example, it might refer to identifying an impending failure that we've had happen before. We want to learn how to predict if it's going to happen again. Other examples would be an unexpected failure. So every now and then something will fail for a reason that we haven't seen before, but we still want to see if there's any signal, unusual behavior that could predict potentially an unexpected failure. Then there's other things. For example, improved alarms. Maybe we just want to reduce false alarms that we're getting from our equipment. Or even something along the lines of root cause analysis, where we've tracked what happened leading up to a failure, we fit a model to the events leading up to it, and then using the model insights, we work backwards and try to figure out what caused this particular failure to happen and try to take action to prevent it from happening again. So really, it refers to a pretty wide range of potential use cases out there.
Thanks, Dave. And I think that's probably a good spectrum of use cases that we continue to see for our customer base as well. And we recommend our customers think about use cases in a structured manner. And this is a framework that we find useful. It's fundamentally laying out use cases around two dimensions. One is around business value, like how much is the overall monetary benefit that you expect to see if you address a use case. Different tiers to it, low, medium, high. And then the second dimension is a use case complexity. At some point, you may have a data set that is incredibly valuable. However, the complexity of making sure all the data sets are understood, the subject matter expertise, all of that can be pretty significant. So when we map out all the use cases that Dave talked about on this framework, what we recommend is, first of all, for customers to think about where they are in their AI journey. Oftentimes, customers are just starting off exploring AI use cases, in which case it's recommended to focus more on the quick wins towards the lower left of this framework. And as you build more momentum, organizational discipline, as well as understanding of the data sets, you can work your way up towards the more complex data sets on the upper right. So Dave, with this understanding, like, how would you recommend we just start the process?
Sure. So what you don't want to do is just jump right into the data preparation and modeling right off the bat. Best machine learning practice before we start working on any particular use case, we want to establish what's our baseline right now. What's our current process? What's our current best practices? So think about any type of service and maintenance that you do today. For example, think of a simple business rule like get an oil change every 5,000 miles. I mean, that's a pretty good rule for maintenance. And then think about what's the cost associated with your current practices. Is this overly conservative? And are we spending too much on maintenance and downtime due to an over conservative and simplistic business rule? And really, could we improve upon this if we had a better model? Then finally, think about how you could actually get to a better process or a better model using something like machine learning. A couple things to think about. Is there some underlying process that allows us to be smarter about when and how we could intervene? And then second, have we gathered data about that underlying process that we could actually use to build a model and improve on what we're doing now? This kind of high-level planning will help us identify whether the use case we're tackling is simply too difficult, something that's not really a good application for machine learning, something where we're not likely to get much lift, or potentially also identify something that's too easy. I mean, maybe get an oil change every 5,000 miles is good enough, and there's really no need to improve upon that. So you really want to kind of plan out what the likely gain is from this use case before you even get started. Now, if we have reason to believe that we can improve upon our baseline practice, the next step we want to do is to pick an approach. Now, I'm not talking about what type of model. We're not trying to pick a deep learning model or an XGBoost model. What I'm talking about is the type of model: classification approach, regression approach, anomaly detection, or even time series approach. There isn't one way to solve a predictive maintenance problem, so you really want to think about the data you have at hand and the type of problem that you're working on when you go to predict an event or select a process. So a couple things to think about. One, how many examples of failure are there? Is this the failure that we're trying to prevent that happens all the time? Or is it something that's relatively rare? And then you also might want to think about the mechanism of failure. Is this the same thing happening over and over again? Or are we looking at unique events happening in each instance that we've tracked? And then finally, you might want to think about a time dependency. So is there some expected change over time that we want to capture in our model? For example, if we're drilling a well, we'll expect pressure to increase as the bit goes deeper. Do we need to capture that change over time as an expected part of our system and look for anything that deviates from that change that we expect as part of our forecast? So let's take a closer look at each one of these possible approaches so we can think about how we'd identify the best approach to take to a given problem. So in some cases, we may have many examples of failure from similar pieces of equipment. Say, take an example where we have a collection of similar pumps that we've been monitoring for months or even years. Here, also, we expect the mechanism of failure is repeated. So maybe the issue is just caused by bearings failing. We could train a model to learn what signal readings indicate normal operation and what signal readings could potentially indicate an issue. What we're doing is we're taking a classified supervised machine learning approach. We're using past labeled examples of failure. What we're trying to do is train a model to classify normal versus abnormal operation. Now think about a different example. What if we didn't really care why a part failed? Maybe we even consider this part disposable, like a filter. Given attributes like the time of year, the type of activity that was occurring, we predict how long we'd expect this filter or piece of equipment to last before needing to be serviced or replaced, what is often referred to as predicting remaining useful life. Now, the goal here isn't to classify normal versus abnormal operation. Rather, we're really just trying to understand when we would need to replace the part. Alternatively, we could turn this around and say, instead of saying, when do we expect to need to replace it, we could say, over a given time window, how many of these parts do we expect to need to replace, given operating conditions and other predictors? Now, some instances, the failures or issues that we're working with are too rare, and maybe the type of failure varies too much for a supervised approach to work. There simply aren't enough examples of our target failure to effectively train a model from. Now, if we still have enough examples of normal operation, we could use an approach called anomaly detection, where we generate an alert for operation that isn't following normal patterns. So in this example, we train an anomaly detection model on a history of normal operation, so it can characterize what's normal operation and then potentially identify what isn't. But the caveat here is that this approach is really tricky. So for one, just because operation is anomalous doesn't necessarily mean that there's an issue. It could just be novel operating conditions that your model has never seen before. You need a fair amount of normal training data to have the model learn what's normal operation and what isn't. If your real issue at hand is that you just don't have many training examples, well, then machine learning may not be the best approach. You still are going to have decent training data to train a model on. And another thing to think about is you're going to want to hold out some actual known failures that have happened in the past to see if the anomaly score generated by the model that you fit actually has some real world meaning and could have been associated with some of the past failures. It's just a way to gut check your model to see whether it's an approach in general that's going to work. Now, there are other examples out there. Take, for example, a use case where we actually expect our signal to vary over time. Change in the signal over time is not necessarily a cause for concern as long as it follows an expected pattern. What we might do here is fit a time series forecast model to predict normal expected change over time. And then if there's significant variation from the forecast, it could be an indicator that something's gone wrong. So let's take an example here. Say we're trying to detect leaks in a drilling operation. Now, in practice, what they're doing is they're modulating the load on the drill bit, measuring the pressure downhole from some type of drilling fluid. Now, as you modulate the pressure, you can expect some kind of delayed modulation in the pressure of the fluid in response to pressure on the bit itself. Push down, and after some delay, pressure increases. Now, you could train a time series model to learn this delay and learn the forecast pattern here. Then, if pressure were to drop suddenly at a time when you expected the pressure to have increased, it could indicate that you have a leak or even a rupture. Now, this is a trickier approach because it would require some real-time monitoring, and it may not be possible to use in all situations. But it's just an interesting idea to have out there. So we've kind of thought through high-level approaches to framing a machine learning problem built around predictive maintenance. What I want to do now is I want to work through an illustrative example, an example of preventing pump failures, to think about first how we might want to frame this problem, how we might want to prepare the data for the problem, how to label our target, and then finally, how we're going to partition our data when we go to validate our model. So to think about the use case, it's motivated by pumps occasionally failing unexpectedly and needing to be replaced. What we want is a warning of an impending failure so the pump can be repaired rather than being replaced and save money that way. Now, the training data we've gathered is sensor readings from a large number of similar pumps scattered around our operations that have been monitored for a steady period of time. Now, if you look at the characteristics of this use case, it looks like a pretty good candidate for classification. We have a lot of repeated examples that we could learn from and then generate predictions going out on future pumps that are in operation right now. So let's visualize what the data might look like in this particular use case. Here, I'm just showing simulated data from a single sensor. In practice, we may have data collected from multiple sensors, but let's just imagine we're looking at one in isolation. There's a few different things going on with the pump. One, you've got normal operation when really nothing was going wrong, things were operating as expected. At the end, in this particular labeled example, we knew the pump failed, it broke. If you think about it, there's really no reason to build a machine learning model to predict whether a pump is broken or not. That's not useful. By the time your pump's broken, it's too late. What we're trying to do here is intervene prior to the failure and understand if there's any signal prior to the failure that we can use to schedule maintenance interventions and reduce pump replacements. So what we're actually looking to build a model to predict is this yellow region, the series of events that happened prior to the failure, not the failure itself. The next thing we're going to want to do, we've identified what our target should be. Now we want to look at what our predictors could be. Now, in this case, we probably gathered a fair amount of IoT data, which comes in as what looks like time series data, right? I mean, it's real-time logging with a timestamp and everything of events from different sensor readings. But we don't necessarily have to set this up as a time series problem because we aren't necessarily looking for change over time that we're looking to forecast. So instead of building out a time series forecast, what we might do here is take our training data and start slicing it up into blocks of time. And then in each block of time, extract features of what was going on in that block of time to get signal. Now, what's an appropriate block of time? Well, that's going to vary by the use case. What I would encourage you to think about is, how am I reacting to this particular system? If it's a piece of machinery, maybe working on a factory floor, I might be able to react to an issue within minutes. And so slicing up my sensor data into 1 minute or 5 minute blocks of time might work really well because I could react right away to an alarm. But you might also imagine maybe you have a truck out in service. You only get data back from it once a week or maybe once a month. You couldn't really react within 5 minutes if something were to go wrong. What you really want to do is, when you do regular check-ins, decide, should we take some preventative action to prevent issues from happening and prevent a failure from happening while this piece of equipment's out in service. So then your block of time might be weeks or even months. Regardless of the block of time that you picked, what you're going to want to do is start extracting features over that block of time. For example, what was the minimum sensor reading or the maximum sensor reading? You could look at the average sensor readings or even standard deviation. And you're going to want to get creative here. So one example is, instead of just looking at min and max, maybe you could also count the number of times a signal reading exceeded the threshold. Imagine something along the lines of how many times did they redline the engine. You might also look at cumulative features. For example, at each time step, what was the total runtime or total amount of miles that were added up during this time block? Another thing you might look at is equipment alarms. We could do a count of alarms, types of alarms that appeared, a lot of different ways you could frame it. And get creative. You can collect operator notes. I mean, the free-form text, nice thing about modeling with DataRobot, it can handle free-form text. Rather than reading all these notes individually, what you could do is collect them, feed them into a model, and just add them to your predictive model to see if you can get out of ahead of an impending failure. So if you imagine the way this process works, what we've done is we've taken our time series data, we've sliced it up into blocks of time. And in each block of time, we've extracted features about events that occurred in that block of time. Those features become a row of data. Each block of time is a row. So you can imagine here, we've taken this particular series and we sliced it up into 6 rows. And we've labeled our target. Everything in green was normal, healthy operation, really nothing to be concerned of. But anything that happened in this final step, when it was time to intervene, we'll label as 1. That's our target. And this helps to understand how we took maybe a large amount of real-time IoT data and formulated the issue or formulated the problem setup as a classification problem.
So Dave, you mentioned a few times interpreting what the data is telling us and making decisions based on that, how to proceed. Can you talk a bit about what's the subject matter expert's role in this process so far?
Yeah, absolutely. So actually, let me take a couple steps back to this feature engineering table, because I think this really illustrates why it can be so helpful to bring in subject matter experts in planning out these use cases. The more creative you can be with the features you're extracting, the better signal you could potentially get and the better predictive model you can build. Subject matter experts are going to know the equipment really well. They're going to know the types of events that are likely to be associated with failure. And they're going to be able to help you guide your decision making in what features should I extract. They're ultimately going to turn out to be predictive features when I fit my model. So this is a great time to involve subject matter experts. At this point, we're not really worrying about the machine learning itself. We're not really worrying about the model fit and the model tuning, deployment, and all of that. We're really just thinking about what's happening in our system that we want our model to learn. So one last consideration to think about, and this comes up quite a bit in all types of machine learning use cases, but especially in many IoT and predictive maintenance use cases. There's a hazard that our model could be overfit to events that are specific to one piece of equipment in our training data, and it won't generalize well to future events. So take, for example, our example we're working through with a large number of pumps that we've been tracking. Sure, the pumps should all be pretty similar. They're from the same manufacturer and operate about the same way. And we also expect that the mode of failure is the same and being repeated over and over again. However, there's always risk that we could have a model that learns a specific pattern to one particular pump's mode of failure that's not going to generalize well to other pumps, maybe located in other regions, other facilities, and so on. So when we divide up our data between training data, validation data, and holdout data, we want to keep samples from different pumps separate. So each pump has a trend history. We'll take a group of pumps and their trend histories. We'll lump it together in our training data. We'll take a separate group of pumps, lump them together in our validation, and then a third group of pumps and lump them together in our holdout data. This is just a guardrail to make sure that our model isn't overfit to one particular event and will generalize well in the future. So that covers a lot of the model setup. We've gathered our data, we've prepared it, we've identified our target, we've thought about how we're going to set it up. We go ahead, run it through DataRobot, have it select a model that fits this particular system well, deploy that model, and we're good to go. Here's the thing, data drifts over time. Now this is true in many use cases, it's true in any industry, but this is especially true in a lot of predictive maintenance use cases. Think of things that can change. For example, oftentimes manufacturers will push software updates to individual pieces of equipment that they've provided you, and that can include things like column labels changing. They may change the names of the different points that you're monitoring on your equipment. It could potentially throw a model off. You could also have novel operating conditions. So it's important when you're setting this problem up to think about, am I capturing all the different seasonal conditions that my equipment's going to be operating in? Have I captured all the different operating conditions and different processes we use? And we're going to want to make sure, as best we can, that we've captured all those different situations. However, the nice thing about monitoring feature drift is that we can check to make sure that there isn't something unexpected emerging in our test data or in our real-time data that we're scoring that deviates from what we trained our model on. This is a common pitfall in predictive maintenance use cases, and it's something really, really important to pay close attention to make sure that your model is actually useful and helping you decide on preventative interventions that aren't actually causing either excessive interventions or cause you to potentially miss a failure you should have caught otherwise.
Thanks, Dave. I think this was really helpful to go through a use case, identify the various steps. So we'll do a quick recap. So in terms of a process, the first question is picking up the right use case. And we talked about focusing on some quick wins before tackling more complex cases. The second step, establishing a baseline. And as Dave mentioned, identifying and evaluating what's being done today, what is the current process, so that you can target an improvement off of that, hopefully measurable by KPIs, business value, cost savings, all of those elements. And then if we get into identifying the exact type of model needed, there were four kinds that Dave talked about: classification, regression, anomaly detection, as well as time series. So each of them has its own considerations in terms of how the data should look like, what kind of analysis is needed before you kickstart an AI use case on that kind of modeling. For the particular model, identifying the data set and then preparing it, which usually breaks down into the target selection, feature engineering, as well as partitioning and associated questions. The next step is modeling, and this is where DataRobot platform automates a lot of things that a typical modeling phase would involve. For most cases, autopilot, a functionality within our platform, would enable you to go through the modeling steps. However, if there are some changes, then you always have the ability to customize and add some custom code as needed. And then finally, as Dave mentioned, model monitoring, which is where you monitor for model drift, systematic deviations that you should account for, and hopefully retrain the model or make minor tweaks. So is this a good representation, Dave? Anything you'd like to add?
Yeah, I mean, you see this whole process end to end, and I hope it becomes clear why it's so important to really plan out your use cases before you just start tackling them. Inevitably, especially when you're dealing with IoT data, there's going to be data preparation involved, and that's time intensive. And you're also going to have to think about how am I going to deploy this model and integrate it with my existing process. So really qualify your use cases first, think about how you're going to set them up, and then start modeling.
Yeah, and as you rightly pointed out, Dave, the business context matters a lot. At the end of the day, it's actually a business process change that we are impacting, and hopefully that's how we get the business value, whether it's cost savings, asset uptime, or other benefits that we talked about before. Well, I think at this point, we'd like to take some questions.
Yeah, so I have a few questions here. So I'll just start with the first one. And so this is around service and maintenance records. I have a person who has these that are generally handwritten. So any recommendations on how to handle that, or a model that would consume that?
Yeah, so there's a couple of things you want to extract. I mean, at the end of the day, it's probably the information and the text itself that's most valuable. So some type of OCR process where you could read the handwritten notes and convert it to actual natural language text would probably be the best. I mean, you could take an image classification approach and see if you could extract information from the images themselves, but really what you're looking for is information in the text, and so I would take an OCR approach.
Yeah. And just to add to that, maybe there's also a bit of parameterizing the information. Obviously, it's free-form text, which can mean a lot of different kinds of notes taken by service and maintenance people. So just parameterizing it and calling out the main points captured, and then, of course, building that into the model. So.
All right. We have a question around human error, seeing a lot of events which happen because of operator making a mistake. So how do you account for that in these models?
I think ultimately, when you think about that yellow region in your training data, the events that occurred prior to the issue, that's essentially what you're trying to characterize. So it's not necessarily all mechanical issues. It's not just, say, vibration from a bearing starting to wear out. There could be things that you could capture that indicate a potential operator error. For example, the identity of the operator who's operating the piece of equipment. Sometimes they're less experienced people, for example, are more likely to be associated with some type of issue. And so it's something that can be incorporated into your risk score as to whether you expect an issue to occur down the road. So I would just think of it really, whether you're trying to extract anything from operator behavior, it's just another feature engineering step. You're trying to pick out what events are indicators of risk and which events aren't.
All right, and this is probably still looping into the data engineering stream of questions that we're having, but I have a question from someone where they've had an asset for quite some time, 10 years, and they do not have a factory baseline. So any recommendations on how to handle those types of situations?
Yeah. So I think this is a interesting situation and sort of a fairly common for industrial assets, which have a significant longer lifetime, often running into decades. The recommendation for us is, from ours is, look at where things are today. Like, what is the maybe the cost structure needed to support the asset? What is the TCO and the different elements within that? Once you have that established in clear, measurable terms using metrics as well as performance, it's easy to then talk about what improvements can be achieved off the baseline. So we highly recommend having a baseline. Otherwise, it's hard for all of us, to go back to our stakeholders and show them demonstrated improvement. But how we draw that baseline could pretty much be a line in the sand you draw today based on what's available. And of course, subsequently, as you improve your process, you move up the maturity curve, you can think about a new baseline and then target improvements of that.
Okay, I have a couple of questions here that are related. One's around no failures, one's around a few failures, but basically dealing with an imbalanced data set in these types of predictive models. Any suggestions on how to deal with situations where there are no recorded failures, or it's just it's a limited set?
Yeah, if we had an instance where we really didn't have any labeled failures, that kind of gets towards the anomaly detection approach as maybe being one of your options. And I really want to encourage folks to be careful before diving into this approach. It's not a silver bullet that's just going to magically identify future issues that have never happened before. It's just a technique that can pick up on unusual behavior that might be predictive of future issues. But really, if you don't have many labeled examples, a couple things to think about. Is there enough training data giving us normal operation that we could still take a classification approach to distinguish between normal and abnormal operation? A really imbalanced data set's fine. A lot of machine learning applications, I mean, think about fraud detection. It's inherently a very imbalanced problem, and that's fine with predictive maintenance too. But if we really only have 1, 2, 3 examples of a failure, then that limits our options. And it might be something you think about when qualifying a use case early on. I wouldn't assume that just because anomaly detection is an option on here that is one you should necessarily invest a lot of time in. Machine learning just may not be the best solution when you have very few examples of failure to work with.
Right. And then let's see, we have one here around, let's see, so a situation where you have to scale this across multiple assets that may be spanning multiple geographies as well. Any challenges that this person should be aware of, or recommendations on how to tackle such challenges?
Yeah, maybe. Yeah, so that's actually a great question. Let me use an example to illustrate. So for a number of our transportation equipment fleets, a customer can have multiple fleets across various geographies. And oftentimes, the assets themselves, for example, a transportation bus can have engines from different OEMs, different equipment owners, etc. So obviously, how we build models is going to be dictated based on what does that distribution look like. For example, you have a fleet running in fairly warm, humid atmosphere that has inherently a certain kind of model that you would need. In addition to having individual equipment level models, you would also need to have an overall asset model. And I think at some point, this question becomes a challenge in terms of how much effort are you willing to spend and how much benefit can you hope to achieve. At some point, if you have like hundreds of models, operationalizing it can become a significant challenge as well. But again, all of that is from the business lens. So from the technical lens, Dave, would you like to add to this?
Yeah, I really like this example because it's where mechanical engineering and data engineering kind of meet. You think about all the different operating conditions and all the different situations that could be encountered. You may want to look for a balance between different models that are specific to different situations versus kind of one catch-all model you could deploy widely. So Now, there may not be an obvious answer as what the best way to split up your models are. Should you do more than one model or just kind of stick to one general model? Really try both. Kind of look at how well a model can predict in different operating conditions. So maybe you have a wintertime model and a summertime model, for example, and that gives you enough lift to justify building two separate models. Or maybe you can generalize well enough based off using something like temperature as a predictor, and one catch-all model works well enough.
Okay, and I think the last one here is around the pump example that you gave earlier. Is a question around which target variable was used, and I think more specifically, kind of what was the logic or the reason for selecting that target variable?
Yeah, it's really interesting when you grab the trend data. The pump unfortunately does not bother to label itself when something is going wrong, and so oftentimes you get a series of trend logs that show pump was working, maybe something was going on, and then pump stopped. And so you have to take that kind of raw log data and work back and identify, well, really what region of this data should I identify as my target if I want to be proactive as opposed to just reactive. So there's a lot of considerations, and you can't just take the raw data set and decide everything after the failure is my target and let's go. You really kind of want to think about, maybe consult a subject matter expert to think about, when did the likely signal for this issue start to emerge? And when should we identify what our target or positive class is versus our normal operation negative class is when training our model?
Okay. All right, that pretty much wraps up the question and answers. I guess if we could move to the next slide, then just want to highlight our community page. You can find all these webinars, this and prior ones that we've recorded on community.datarobot.com. But not only is community a place where you can go and watch webinars and ask questions, but it's really a learning center where you can engage and learn from others, both peers and customers of ours who are asking questions, interacting, but also with the DataRobot experts as well. So we have people on who will respond back to you and really help you build out your own knowledge base and help you accelerate your AI solutions as well. So please go and check that out, community.datarobot.com. And if you have any other questions, again, the email is aisuccess-webinars@datarobot.com. And with that, thank you very much for your time.